Right, so today let's talk about my favorite subject in all of science, and that's thermodynamics. So we'll start the discussion with thermodynamics, and afterwards we will talk how it is applied to chemistry. And the title of the chapter in the book is Thermochemistry, because that's thermodynamics application in chemistry. But the beginning of it is just regular thermodynamics. If you take thermodynamics after this class, you will see all this stuff again later on. I will let you know when we switch over to thermochemistry. But the bulk of this is going to be thermodynamics. So let's go vague and meta. Energy, what is this? It's this thing that all objects have and that they can give and take from one another. Oh, and you can't destroy it or create it either. Got it? Good, me neither. All right, let's go pretty simple. We'll say energy is this sort of heat that you can exchange between bodies. We can use it for our benefit or not. And we have several types of energy. And I'll discuss several of them. So you have chemical energy, which is this heat between atoms and molecules. So if you break apart a bond, you'll release energy. So that's the type of energy there. You have potential energy, and that's sort of like energy related to position. That's the most common way of thinking about it. So an object that is placed higher has more of a potential to fall than an object that's placed lower, and therefore an object that's placed higher has higher potential energy. There are other types of potential energies. For example, you've all seen it when you wind up a toy, right? You squeezing this spring, you're winding it up and winding it up and winding it up. There's this sort of feeling, even I'm sure when we feel it, it's sort of like it's going to pop any second. I just put so much, I squeezed so much into it that it could easily just pop. That's sort of like the idea of potential energy. You know, you taking say two magnets that hate each other, the two poles that are the same, right? And you squeeze them together anyway, and you feeling them resisting it. That is potential energy, because as soon as you let go, it's going to go. So there's a lot of different types of potential energy, but for the purposes of this course and probably for regular thermodynamics, just think of it as position. Something that's placed higher has more potential energy because it can fall farther. You have kinetic energy. That's the energy of motion. So things that move really fast have higher kinetic energy. And there are other types like mechanical energy, electrical energy, nuclear energy, and internal energy. And we'll discuss internal energy in a bit. So energy sources abound. We can get energy from natural gas. We can get it from coal. We can harvest it from the sun or the earth. We can extract it from wind and water. And we can also get it from nuclear and chemical processes and from combustion. There's a lot of different types of sources where energy can be gotten. And the SI unit for energy is the joule, which is basically Newton times meter. In chemistry, we often use the calorie, which is defined as 4.184 joules. It's just a legacy unit. We very often use joules, but sometimes you'll see calories. You also see calories when you're discussing foods. Nutrition facts are labeled in calories, and this is where it's coming from. Sort of like the energy you can extract in your body from the food is labeled in calories, which you can also label in joules. And in our wonderful, wonderful, flawless system, BTU is the unit for energy, which is British thermal units. By the way, I was being cynical. So energy can be stored energy, or it can be transferable energy. And so while I can transfer all energy, some of it is going to be more tightly bound to the object, and we call that stored energy. Largely, it's the energy of motion, kinetic energy, and position, which is potential energy. And this is how you would calculate that. Kinetic energy is 1/2 times the mass of the object times its velocity squared, right? So you can figure out your own mass, right? And then if you run at like 3 miles an hour, you can multiply your speed squared by your mass, and you can get your own kinetic energy. Potential energy here is related to the height of the object. I'm brushing over this really quickly because this is a physics thing. We're not going to do much of it here. Potential energy is mass times the gravitational constant, which is 9.81, and delta Z is the height difference. So the higher something is, the higher this delta Z is. When you take physics, you will likely see this. Okay. There are other types of potential energy I mentioned. We talked about magnetic here. When you put two magnets against one another, we talked about springs. There's also chemical potential energy and electrical potential energy. There's a lot of other ones. These are some of the most common ones. Okay, on the micro level, right? This stored energy is known as the internal energy, E, and we denote it with E, and it is simply the sum of all the kinetic energy and potential energy of each one of the molecules, which is a pain in the tuchus to calculate. You can't just go do that. It would take you forever to do that. Every single atom and every single molecule and every single substance that you're dealing with has to be calculated. How fast is it going? How far is it from hitting the ground and all that, and so on and so forth. So it is not largely done, right? There's another term that I want to discuss, and that's enthalpy, H, and it is the internal energy due to flow. So if I'm flowing something, it's H is equal to E plus PV. Okay. So is your head spinning? Too many energies? Let's summarize it. Okay, 1. Energy is like heat-ish. Okay, it's not exactly heat, but think of it as heat. All right. 2. Energy can move from one body to the next. You can just transfer it from one to the next. You can't just at will create it. Energy is this thing that we have to conserve. There's only a finite amount of it. There's a lot of it, but there's only a finite amount of it. 3. Energy can be stored or transferable. We haven't discussed transferable. Don't worry about it for the moment. It can be stored. If it's stored, what is stored energy? Well, it's the sum of kinetic energy, which is stuff that's moving, okay, plus potential energy. If I'm looking at a TV hanging on a wall, it has 0 kinetic energy because it's just hanging there, but has a lot of potential energy. It can fall on someone. A car on a hill has both high potential energy because it can fall from the hill, and it has high kinetic energy if it's driving. A parked car on a beach has very little stored energy. It's not moving. It's just parked. And it's on the beach, so it's at sea level, so it's got very low stored energy. Okay, so got it, that's stored energy. So that's in the physics realm, but we're dealing with chemistry, so we're going to go on micro level. Micro level, I can treat every atom or every molecule as this car of ours. If it's up, it's at the beach, or if it's up on a hill, whatever, I can calculate the Ke and the Pe for that, and when I add them up, I can add them all up, and that's the internal energy E, or sometimes you'll see it as U. That's why I put U here. It's interchangeable, U or E, doesn't really matter. So that's the internal energy. It's basically the kinetic energy and the potential energy of every single atom, of every single molecule in your substance. Okay, you can't calculate this U or E thing by yourself. It's a pain to do. It's too many variables, too many things to deal with. So we don't. So we look it up in tables. We calculate that using equations, which you won't in this course. Blah blah blah. So don't worry about figuring that out. I'll usually give you the internal energy. When stuff flows, like if you have a river or something like that, or if you have a gas that's flowing around, it's more useful to talk about H rather than the internal energy, which is, it's very similar. H is equal to internal energy plus PV, pressure times volume. Okay, so hopefully that you got that. That's basically the whole shtick with thermo. That's it diluted down as much as I can. Hopefully you understood that. Let me know if you didn't. I will elaborate on whatever you didn't understand. But that's basically the whole shtick here.